The inference that we're going to start with is estimating an unknown parameter based on numbers in a random sample. And we'll start with a recapitulation, remembering what has gone before. And the first thing that I will make clear always is the assumption about sampling. We're going to assume that we have a population which you should imagine to be very large, and that we have a simple random sample from that population, that is draws at random without replacement. The simple random sample is large, but still small relative to the population, and you will recall this was the typical situation in polling where the correction factor for the standard error was close to 1. And if you've forgotten all that, please go back and look at 2.2, sort of near the end. So, for example, you're sampling a few thousand out of hundreds of thousands, or certainly out of millions. And let's do a calculation which we had done before. When you are sampling a relatively small number out of a large number, then whether you are sampling with or without replacement doesn't make much difference. So you're not badly off thinking about all of this sampling being done with replacement, which certainly makes things easier in the sense of being able to use independence. Here's a question which you could have answered several weeks ago in 2.2x. You've got a large population. I'm not going to tell you how many, it's just large. And what was our agreement in 2.2? If I just say that, I'm giving you dispensation to assume it's so large that that correction factor isn't going to matter for the standard error. So a large population, and I know everybody's age. And the average age in this population is 37 years, and the SD is 15 years. Now I'll say this. If I already know everybody's age, and I am taking a sample, a simple random sample of 200 people, and I am asking you for the average age in the sample, I am being a probabilist. I am doing probability theory. I have a large population. I already know all the data in the population, or at least enough. And I'm trying to predict what the sample will turn out like. The statistician has the opposite problem. The statistician never starts out knowing the average in the population. For now, we are going back to 2.2, where we are probabilists. We know what the population looks like. We're trying to say what the sample is going to look like. All right, so what is the average age that you expect in the sample, and can you put a plus or minus number on it? Well, you know how to do this. The average age that you expect in the sample is the same as the average that you saw in the population. This is an old 2.2x fact. And so in the sample, you expect the average age to be 37 years, but you know it's not going to be 37 years. It's going to be a little bit off. Why is it going to be a little bit off? Because of chance error. The people you get in your sample are a random set. If you took a different sample, you'd have got probably a different average. So there is chance error involved. You're estimating 37, but it's going to be a plus or minus a little bit. What's the plus or minus called? It is called the standard error of this sample average. And how is it calculated? Well, it's calculated by a formula. It is calculated by a formula that says you take the SD of your population and you divide by the square root of the sample size. Sigma over root n, which you have used over and over again. And so if I write that down in this case, the SD of the population is 15 years. You divide by square root of the sample size and you get just about 1 year, a little bit more. So in your sample, you expect to see an average age of 37 years, give or take about a year. And what do I mean by give or take about a year? Well, that's a standard error, so you know that you wouldn't be surprised to find something in the 36 to 38 range. You wouldn't be surprised to find something in the 35 to 39 range, maybe 34 to 40. Beyond that, you start to get very surprised, because when you have the sample average of 200 draws from a population, that distribution is roughly normal. Those sample averages, their distribution is roughly normal regardless of what the population is that you're drawing from. That's the central limit theorem. And so you expect to be able to go out 2 standard errors, 3 standard errors, 4 standard errors is very, very surprising. So those are all going to be useful ideas to remember, and it is going to be important to remember also what this 1.06 years measures. It measures the difference between this population average and the actual sample average that you're going to get. The SE of the sample average measures the rough size of the difference between the population average and the sample average. There are two averages in this picture. So you should imagine in your head a long list of numbers, that's the population, it has an average, and then a shorter list, that is the sample, and it has an average. These two are not the same. They differ by roughly this much. Small multiples of that much. So this is nothing but recap. Well, now let's turn this around and turn into statisticians. I have a simple random sample of 100 people that I've taken in a city. And in that sample, I'm looking at an average age of 38 years and an SD of 14 years. So those 100 people, their average age is 38 years. The question is, what's the average age of the people in the city? Do you know it? No, you do not. You haven't gone to everybody in the city and asked their ages. You've gone to 100 people and you've asked their ages. Those people's average age is 38. If you went to everybody, what would you estimate that average to be? And can you give us a plus or minus? Well, you can certainly have a pretty good try. You know that with a simple random sample, the sample average is expected to be roughly the population average. So if you had to guess just one number, somebody's saying, I'm only giving you one shot, guess the average in the population, you're going to say, well, you know what? I saw 38 in my sample, I'm going to guess 38 in my population. And the reason you are doing that is you can actually put a margin of error on that. You can put a plus or minus number, which is the same old friend, SE for the sample average, which measures how far this sample average is, or this generic sample average is from the unknown population average. And how do you calculate that thing? Well, you take the population SD and divide by square root sample size, sigma divided by root n. So let's do that. Root n is root 100, I've got it. What is the population SD? Is it 14? Don't think so. Might be, but might not. This 14 is the SD of the sample, is the SD of these 100 people. So if I really, truly, hand on heart, have to calculate this standard error for the sample average, all I can say is this. It's something I don't know divided by the square root of 100. And I can fold my hands and be very virtuous and I'll be completely right. But I'll also be very boring and very useless. So what am I going to do? Well, I'm a statistician, I'm going to estimate. What do you think is a reasonable estimate for this number? Well, what do you have? You have a random sample of 100 people. You've got a large random sample. Why did you take a large random sample? Because you think it's going to look like the population. And you're already telling me that its average kind of looks like the average of the population. So how about, yes, exactly. This SD is an approximation to the population SD. And so now not equal to, but approximately equal to, where I should have the population SD, I'm plonking in the sample SD. Divide that by root 100 and I've got 1.4 years. And so the 1.4 would go over here. And what has happened here? If you look at all of this, you're estimating an average in the city and you've got an estimate, and you are also, look at this word about, you are also estimating the size of the error. Because the size of the error has two ingredients, the sample size, which you've got, and the population SD, which you don't have. You're estimating from the sample. So how good is this thing as an estimate? Well, let's take a look. First, I have to give you a name. The bootstrap method, a wonderful American name for a technique coined by Brad Efron in Stanford. And it comes from the expression lifting yourself up by your own bootstraps. You're on the ground, you can't get up. What you do as a tool to get yourself up, well, you pull yourself up by your own bootstraps. And so here I am, I need the population SD. I don't have it. What am I going to use? I'm going to use what I've got, which is the sample SD. So this is a summary of what we said before. Your large random sample looks like the population with high probability. And so you use the sample SD as an estimate for the population SD. And in the end, it's not just the 14 you're using. It's not the SD you're ending up with. You want the standard error of the average. So what do you do to that 14? You divide it by something rather large. You divide it by square root of sample size. And so in the end, the error in the SE, this is an estimate. But it's a pretty good estimate because whatever error you've made in the numerator, you've kind of killed that by sticking in root n in the denominator. And that's the important thing to note. All of this can be made very precise mathematically, and we don't have the time or the techniques to do that, but at an intuitive level, this is the way to understand why this 1.4 is a decent estimate of the standard error for the sample average that you want over here. Now it helps some people to see a more formal treatment, and so I will do a formal treatment, exactly the same problem. I've just cut and pasted it from the previous page. And the model, the mathematical or probabilistic model, is this. Each member of the population holds a ticket showing his or her age. So I've got all of these people, and I have thrown away everything about that person except the person's age. In other words, I have converted all of those wonderful people into numbers. I am a statistician. That is what I do. So each person now has been replaced by his or her number. And that's everybody in a city. That's a lot of people. And so that long list of numbers has a mean, which we in 2.2x were calling mu. Mu, Greek m for mean. That's the number we don't know. And by the way, we don't know the SD of that long list either. What do we know? What we've got is a sample from which we are trying to estimate the population mean mu. We're trying to get at what the population mean is, and the sample is capital X for random variables as before. The sample size is n equals 100. The sample mean, which we were calling x bar, we know that's its observed value is 38. And the sample SD, which I'll call S, its observed value is 14. It's important to remember that had you drawn another sample, X bar would most likely have had a different value than 38, and S would most likely have had a different value than 14. Not very different perhaps, but different. So these two numbers that you have belong to this particular sample. And that is why you can't just say, well, okay, so I saw an average of 38 in my sample. I'm just going to tell you the average of the population is 38 and I'm done. I can't do that because I am imagining all the other ways my sample could have turned out. And it could have turned out lots of different ways. So I know that 38 is one possible value and a reasonable estimate of the average, but I gotta give myself some room. So I have to give myself some plus or minus. And so the method that we've used to make our estimate is, yes, you start out with your sample mean as your estimate, but then you attach the standard error to it, which is sigma over root n, which is this unknown population mean over square root of sample size. We don't know that. So we notice that it's going to be around 14 with high probability, and so your standard error is going to be close to S divided by square root of n. And numerically, that means your estimate is 38, give or take, roughly, not exactly, roughly 14 divided by root 100, 1.4. You're quite right. I have done nothing new on this page than I did on the previous page. I have done exactly the same thing with a little more mathematical notation for those of you who are going to read math books and want to recognize what's going on. Now, this is a list of ages. As you will recall from 2.2, anything you can do for this arbitrary list of numbers, you can specialize to a very important special case, and which is that. Oh yeah, zeros and ones. Proportions. So now, here I am with voters. I have 1,000 voters taken in a city, right? And a city might have hundreds of thousands of voters, possibly in the millions. And in my sample, 37% like candidate A. And so now I'm wondering, well, in this city, what percent are in favor of this candidate? If you had to guess one number, just one number, what number would you guess? Yep, you'd guess 37. And then would you stop there? I hope not, because if I came along and I took another sample, then my number wouldn't be 37 necessarily in my sample, and then, then I'd have a different estimate, and you have to somehow take that into account. You've got one sample out of many samples, so what are you going to do? You're going to play the same game we just played. What is it that we're trying to estimate? We're trying to estimate the percent of voters in the city who favor candidate A. We do not know what that is. We just know the percent among these 1,000 people. So that proportion of the city's voters who favor candidate A, I'm going to call P. We're trying to get at this P. And what do we have as a candidate for this P? Yeah, it's 0.37. And so the estimate of P, just a single number estimate, is 0.37, which is 37%. Give or take what? Well, it's a standard error in this thing, and what was this? This was a sample percent, so I need the SE for the sample percent, or the sample proportion equivalently. How do you find that? Sigma over root n, and what's sigma? It's a list of zeros and ones, and what's the SD of a list of zeros and ones? Aha! Square root fraction of ones times fraction of zeros. It's all coming back from the haze. Sigma over root n, but now sigma is P times 1 minus P. We did this over and over again in the previous class. And so, how much is this? Well, what's P? P is question mark. 1 minus P is 1 minus question mark, and I divide that by square root, I divide that by 1,000, and I take the square root, and I'm done. Once again, correct and useless. So what am I going to do? Exactly what I did before. I'm going to throw in estimates. And what's the estimate of the question mark? That's what we started with. It's 0.37. So approximately equal to 0.37 times 1 minus 0.37 divided by sample size, square root. And that comes out to be just over 1.5%. And so what I'm saying is that in my sample of size 1,000, I saw 37% in favor of the candidate. So in my population, I'm going to estimate 37%, give or take about 1.5%. So I wouldn't be surprised to be off by plus or minus 1.5, plus or minus 3, plus or minus 4.5%, but more than that, I will be very surprised. So this gives you a sense of how accurate your poll is. Once again, this is the bootstrap method. We are plugging in here the number that we have seen in the sample, and it works well because you are making an error up here, but it's getting killed by the division by 1,000 down there. There's one point I'd like to make about polls. Because the list of zeros and ones is simple, there is something you can do to figure out just how good or bad this estimate is, which you can't do when the list doesn't have zeros and ones. So let's just note what we've got. What we've got is a bootstrap estimate of the SE, and that's 1.5%, 1.53% roughly. It's not necessarily exact, right? I'm maybe off a little bit because this question mark could be different. So what is the worst that standard error could be? What is the biggest that it could possibly be? When you have a list of zeros and ones, how big can square root of P times 1 minus P possibly be? When is it biggest? You remember this. Oh yes, you remember this. That's right. When the coin is fair, the standard error is maximum when P is equal to 1/2. And so you know, no matter what, that standard error, the maximum it can be, is square root of 0.5 times 0.5 divided by 1,000, and look at that. That's 1.58%, awfully close. And this 1.58% is called the conservative estimate of the SE. It can't be any bigger than that. Lots of points to note here. First, your text starts out with this one. And so when you read your text, you will be reading in the opposite direction to my lectures. I'm giving you what is normally done. These two aren't that different because really 0.37 is not that different from 0.5. Obviously, if this was 0.01, then I'd have a problem, but then I'd have a problem with other things as well if it was that close to 0%. But what you've learned from this 1.58% is that no matter what the population, no matter what the question is being asked, as long as it's a 0-1 poll, your answer is yes or no. If you have a simple random sample and the size is 1,000, then the error that you make in your estimate of the percent is going to be no more than about 1.6%. So if you look at 1,000 and your city has 8 million people in it, or indeed if 1,000 voters are taken out of a nation which has hundreds of millions of people in it, then even though 1,000 is a tiny proportion of millions, you're not going to make much error at all. 1.5%, roughly 1.6% at the most. And this is numerical justification for how polls can be accurate based on a small percent of the population as long as the number in the sample is quite high.